Before light, there was darkness, not the kind we find when we close our eyes, nor the shadows cast by distant stars. This was a deeper, absolute void universe that had yet to shine. The story of our cosmos is often told starting with a bang, the Big Banga, phrase that conjures images of fiery explosions and brilliant creation. But for hundreds of millions of years after that initial moment, the universe was a very different place. There were no stars, no galaxies, and no light to illuminate the vast expanse. Imagine an endless, invisible ocean of hydrogen and helium gas, stretching in all directions, cooling and expanding in the quiet dark. Astronomers call this mysterious period the cosmic dark ages. It's the time after the initial super-hot glow of the Big Bang faded away. But before the very first stars flickered into existence, it was an age without sunlight, without structure, and certainly without witnesses to observe it. The truly silent dark era. Yet within that profound darkness, something incredible was happening. Gravity, the silent architect of the cosmos, was patiently at work. It was slowly pulling those primordial gases together, gathering them into denser and denser clumps. These were the invisible seeds from which everything we know today would eventually grow: every star, every galaxy, every planet, and even life itself. The stage was being set for the first great cosmic dawn. So how did the first stars form? How did they manage to ignite in such an empty, cold universe? Think of it like a cosmic gravitational snowball. Tiny, almost imperceptible variations in the density of the gas acted as gravitational centers. Over millions of years, these centers pulled in more and more material. As these clouds of hydrogen and helium grew, the pressure and temperature at their cores began to skyrocket. Finally, after an unimaginably long wait, the core of one of these massive gas clouds reached a critical point, a staggering 10 million degrees Celsius. At that temperature, nuclear fusion ignited. Hydrogen atoms began smashing together to form helium, releasing a tremendous burst of energy and light. The first star was born, and with its birth, the cosmic dark ages began to end. This single star was not alone for long. Soon, other massive clouds collapsed and ignited, creating the first generation of stars. These were not like our sun. They were giants, hundreds of times more massive and millions of times brighter, burning through their fuel at a furious pace. They were blue-hot behemoths that lived short, spectacular lives. When these colossal stars reached the end of their lives, they didn't just fade away. They exploded in brilliant supernovae, the most powerful explosions the universe had ever seen. These explosions seeded the cosmos with new, heavier elements: carbon, oxygen, iron, the very building blocks of planets, and eventually, life. The darkness was not just being pushed back by light. It was being filled with the raw materials for a much more complex and interesting universe. Today, using powerful instruments like the James Webb Space Telescope, we are finally beginning to peer back into this enigmatic epoch. We're detecting the faint light from the most distant galaxies, which are essentially time machines showing us what the universe looked like just as it was emerging from the darkness. By studying this ancient light, we are piecing together the story of our cosmic origins, the incredible journey from a silent, dark void to the brilliant, star-filled cosmos we see today. Every atom in your body was forged in the heart of stars that descended from this first generation. Our story began in that darkness, waiting for the light. Ever wonder why the universe, now filled with billions of galaxies, was once completely dark? To understand this, we have to travel back in time, to the very end of the universe's first light. About 380,000 years after the Big Bang, the cosmos was a blindingly hot soup of particles. Light, in the form of photons, was trapped, constantly bouncing off free electrons, like a pinball. It couldn't travel more than a few feet without being scattered. Imagine trying to see through the thickest fog imaginable. That was the entire universe. But then, something incredible happened. As the universe expanded, it cooled down. At around 3,000 Kelvin, it became cool enough for protons and electrons to finally pair up, forming the first neutral atoms of hydrogen and helium. This event is called recombination. With no more free electrons to block their path, the trapped photons were suddenly set free, streaming across the cosmos. this ancient burst of light is still traveling through space today. We detect it as the cosmic microwave background radiation, the oldest light in existence. But here's the catch. This wasn't the light of stars. It was the fading ember of creation itself. Over billions of years, the expansion of space has stretched this light so much that it's now invisible to our eyes, existing only as faint microwaves. So, after this initial flash, the universe plunged into darkness. It entered a long, quiet chapter known to cosmologists as the Cosmic Dark Ages. Space was filled with a thin, uniform fog of neutral hydrogen gas. There were no stars to shine, no galaxies to illuminate the void, just a vast, featureless, and utterly black expanse. But this darkness wasn't perfectly smooth. Tiny, almost imperceptible ripples in density, leftovers from the Big Bang, were scattered throughout the cosmic fog. These were the seeds of everything to come. Regions that were just a fraction of a percent denser than their surroundings began to exert a slightly stronger gravitational pull. Slowly, patiently, gravity began its work, pulling more and more hydrogen and helium gas into these slightly denser areas. Think of it as a cosmic tug-of-war. The expansion of the universe was trying to pull everything apart, while gravity was trying to pull everything together. For hundreds of millions of years, expansion was winning. The process of forming structures was incredibly slow, but gravity never gives up. During this era, the universe was dominated by that neutral hydrogen gas. These atoms don't emit or absorb visible light, making them effectively invisible. If you could have floated in space back then, the sky would have been pitch black in every direction. The only thing moving through the void was that fading, red-shifted afterglow of the Big Bang, far beyond the visible spectrum. This invisible hydrogen fog was incredibly thin, less dense than the best vacuum we can create in a lab. Yet, stretching across billions of light years, it was enough to make the universe opaque to certain wavelengths of light. It was, quite literally, a dark age. For stars to form, this gas needed to not only gather but also cool down. Gravity can only do its job of squeezing matter together if the gas can radiate away its heat. The problem was, hydrogen atoms are terrible at cooling themselves down. They needed help from heavier elements like carbon and oxygen, which act like cosmic radiators. But those elements didn't exist yet. They're forged inside stars. This is the great cosmic paradox that kept the universe dark for so long. To make stars, you need to cool the gas. To cool the gas efficiently, you need elements made inside stars. So the universe had to do it the hard way. It also had a secret weapon, dark matter. Even before the Dark Ages, invisible halos of dark matter had started to form. These mysterious, unseen structures acted as gravitational wells, creating deep pockets where ordinary hydrogen gas could collect. Over hundreds of millions of years, enough gas finally gathered in these dark matter cradles. Squeezed by its own gravity, it became dense enough and hot enough to overcome its cooling problem. Every galaxy, every star, every planet, and even Uzwe all trace our origins back to this long period of darkness. The Dark Ages weren't a pause in cosmic history. They were the essential quiet before the storm. It was the time when the universe was patiently laying the groundwork, gathering the materials and setting the stage for the greatest show it would ever produce. The darkness was the womb of creation. Then, after nearly 400 million years of silence, somewhere in that vast, cold, and endless dark, a pocket of gas finally reached the breaking point. The pressure and temperature at its core became so extreme that hydrogen atoms began to fuse. In that instant, a single point of light flickered to life. A star was born. And with it, the universe began to wake up. The cosmic dark ages were over, and the era of light had begun. From the cold, deep silence of the universe's dark ages, the very first light emerged. It didn't start with magnificent galaxies or vast clusters, but with the smallest flickers of ignition, deep inside immense clouds of collapsing hydrogen. These were the first stars, the cosmic pioneers that would end the darkness and begin an era of illumination we call the cosmic dawn. They're known as population 3 stars, and even though we've never seen one directly, their fingerprints are written all across the universe. So, how did they come to be? Roughly 100 to 200 million years after the Big Bang, gravity finally started to win its ancient struggle against expansion. Within the densest knots of hydrogen gas, clouds collapsed inward, heating up as they fell. The process was absolutely ferocious. As all that matter compressed, temperatures in the core skyrocketed to tens of millions of degrees. And then finally, nuclear fusion ignited. This is the same process that powers our sun, but it was happening on a scale that is almost impossible to imagine. The first stars switched on, but these were not ordinary stars like our sun. They were absolute monsters. Population 3 stars were likely hundreds of times more massive. You see, the early universe was pristine, composed almost entirely of hydrogen and helium, lacked what astronomers call metals, heavier elements like carbon and oxygen. In modern star formation, these metals act like coolants, allowing gas clouds to fragment and form lots of smaller stars. Without them, the primordial clouds couldn't cool down effectively. So instead of forming a whole cluster of stars, these massive clouds often produce just one or a few colossal ones. The result? Stars with masses from 30 to maybe even 300 times that of our sun, burning incredibly hot and blue, with surface temperatures hotter than any star we see today. They lived fast, and they died young. These titans of the pristine universe burned through their fuel in just a few million years, a mere blink in cosmic time. But in that short lifespan, they completely transformed everything around them. They unleashed torrents of powerful ultraviolet radiation, strong enough to rip electrons away from the neutral hydrogen atoms that filled space. Slowly but surely, these bubbles expanded around each new star. As more and more stars were born, their bubbles grew and started to merge, transforming the universe from opaque to transparent. This was the beginning of the epoch of reionization, a gradual, universe-wide takeover where light once again dominated the darkness. But lighting up the universe wasn't their only job. These early stars also started the critical process of chemical evolution. When they died, they didn't just fade away. Many of them exploded as hypernova blasts, far more energetic than typical supernova. Some may have even collapsed directly into black holes, planting the seeds for the supermassive giants we now find at the center of galaxies. Most importantly, their explosive deaths forged the first heavy elements: carbon, oxygen, iron, the raw materials for planets, and eventually, for life. Before the first stars, the universe was simple. After them, it had the ingredients for complexity. Think about it. Every atom in your body that's heavier than helium, the carbon in your DNA. The iron in your blood, the calcium in your bones was forged in the heart of a star like these. They may be long gone, but they seeded the cosmos with all of its future possibilities. As this first generation of stars lived and died, they left behind enriched gas. This new gas, now containing those precious metals, made it much easier for the next generation of stars to form. These second-generation stars were smaller, lived longer, and could form in greater numbers. Clusters of them began to gather within the immense halos of invisible dark matter, creating the first protogalaxy, small, irregular gatherings of light. Each one might have only contained a few million stars. It's a tiny fraction of our Milky Way. Yet these were the first organized cities of stars, the ancestors of every galaxy to come. Over billions of years, gravity pulled them together. They merged repeatedly in a cosmic assembly line, building the vast, magnificent galaxies we see today. In that sense, our own Milky Way wasn't born all at once. It's a grand descendant of countless ancient collisions, built from those first tiny sparks that lit up the cosmic night. While stars and galaxies were forming, the universe itself was developing a grand structure. Simulations show us that dark matter, the invisible scaffolding of the cosmos, was shaping everything. It formed vast filaments, creating a cosmic web that stretches across the entire observable universe. Galaxies weren't just scattered randomly. They formed along these threads like pearls on a string with vast, empty voids in between. This cosmic web is the fundamental architecture of the universe, the skeleton upon which all the shining matter is arranged. As more stars and galaxies lit up, their combined radiation finally finished the job of reionizing the universe. By about 1 billion years after the Big Bang, the fog had cleared. The Dark Ages were officially over. In their place stood a young, luminous cosmos, a universe filled with galaxies forming, merging, evolving in a beautiful ballet of gravity and light. This was the dawn of the visible universe, the beginning of the story we can still read today with our telescopes. Of course, deep mysteries remain. What exactly were those first stars like? How massive were they? How many of them were there? When did that very first light truly appear? These are questions that no human eye has ever directly answered, but our instruments are getting tantalizingly close. The first stars no longer exist, but their light echoes through time. Their radiation sculpted the universe, their deaths enriched it, and their descendants became everything we know and see. Every star that shines in our night sky carries a trace of their ancient legacy. From darkness, they created light. From simplicity, they created complexity. From chaos, they created the cosmos. Even now, astronomers are peering into the deepest, most distant corners of space, searching for the first flickers of that ancient dawn. They're hoping to witness the moment when the universe lit up for the very first time, and finally see the ghosts of its first children. We call it the first light, the moment the universe broke its long darkness. But when, exactly, did that light appear? It seems like a simple question, yet it cuts to the deepest mysteries in cosmology. For the universe, light isn't just illumination, it's history. Every photon tells a story of what existed, how far it's traveled, and what it encountered along the way. And when we search for the first light, we are really searching for the moment creation became visible. If you ask when did the first light appear, science doesn't offer a single date. There was no cosmic switch flipped one day to end the Dark Ages. Instead, the dawn came slowly, infinitely, locally, and chaotically. It began with the first stars scattered across a vast dark universe. Each star illuminated only a small bubble of space around it. When a few of those bubbles grew and overlapped, the first regions of the universe became transparent to ultraviolet light again. But elsewhere, darkness remained. This patchwork transition bright islands in a sea of darkness lasted for hundreds of millions of years. It's what cosmologists call the epoch of reionization. In some regions, stars formed early, perhaps just 100 million years after the Big Bang. In others, conditions weren't right until hundreds of millions of years later. So, when did first light truly appear? The honest answer is, gradually. Between 100 million and 1 billion years after the Big Bang, the universe transformed from a foggy darkness to a transparent, glowing cosmos. But the details, who lit the first candle when, and how, remain hidden in that distant past. Astronomers still debate which objects produced this earliest light. Were they the massive population 3 stars, living fast and dying in powerful explosions? Or did early black holes, the remnants of those very stars, secrete gas and shine as brilliant quasars, outshining entire galaxies? The truth probably involves both. In one theory, the first stars, enormous, short-lived, and fierce, were the primary engines of reionization. Their intense ultraviolet light ionized the hydrogen gas around them, creating growing spheres of transparency. But there's a problem. These stars died quickly. To keep the process going, new generations had to form continuously, which means early galaxies must have been surprisingly efficient at birthing stars. A second theory argues that the earliest black holes powered the dawn. As gas spiraled into them, it heated to millions of degrees and emitted powerful X-rays, which could ionize hydrogen over much larger distances. If true, the first light of the cosmos may not have been starlight at all, but the glow of matter falling into black holes. It's likely that starlight ignited the first sparks, while black holes amplified them, slowly transforming the universe into the luminous web we see today. To truly solve this mystery, astronomers are looking not for visible light, but for radio shadows. Neutral hydrogen, the element that dominated the Dark Ages, absorbs and emits radio waves at a specific wavelength, 21 centimeters. This is the key to unlocking the cosmic dawn. As the first light appeared, the hydrogen gas began to interact with this 21 centimeter signal in distinctive ways. By mapping this signal across the sky, scientists hope to watch the Dark Ages end to see the universe's light switch flicker on in real time. But there's a massive challenge. These signals are incredibly faint. Earth's own radio noise, our satellites, and even FM radio stations easily overwhelm them. Detecting this ancient signature requires extraordinary sensitivity and complete isolation. Projects like LAW and the Square Kilometer Array are attempting this feat, aiming to capture a faint dip in radio frequencies that could correspond to the moment the first stars turned on. In 2018, the EDGES experiment claimed to have detected such a signal, a mysterious, unusually strong absorption feature that might correspond to the birth of the first light around 180 million years after the Big Bang. If that signal is real, it would mean the first stars formed even earlier than we thought. But the result remains controversial, awaiting confirmation from other observatories. Even with our most powerful telescopes, this earliest epoch remains beyond our direct view. The universe's expansion has stretched the light from those first stars into infrared wavelengths visible to human eyes. Until recently, the farthest galaxy we'd ever seen dated to about 400 million years after the Big Bang. But the James Webb Space Telescope has pushed that frontier closer to the beginning, spotting galaxies that may have existed only 250 to 300 million years after the Big Bang. Still, these are not the very asterisk first. Somewhere before them lies an uncharted period, twilight between darkness and dawn that no telescope has yet seen. These hidden epochs are like lost chapters in a book we can almost read. We know what came before the Dark Ages. We know what came after the luminous universe of galaxies. But the middle, the instant when the lights first came, on remains one of the greatest frontiers in science. And here lies the cosmic paradox. The first light of the universe, the most important turning point in its history, is the hardest to see. It's not because it wasn't bright. Those early stars and black holes were blindingly luminous. It's because time and expansion have stretched and dimmed their light beyond our easy reach. Imagine watching a bonfire from across a vast ocean. By the time its light reaches you, it's just a whisper of faint warmth, buried beneath waves of noise. That is how we see the early universe today. We may never directly witness the first star ignite, but through the glow of ancient galaxies, the whispers of 21 centimeter radiation, and the deep infrared gaze of our best telescopes, we are slowly learning to reconstruct that lost dawn. But even as our technology advances, profound mysteries remain. When exactly did the first star ignite? How massive were those first stars, and what became of the first black holes? Some may have merged, forming the seeds of the supermassive black holes at the centers of galaxies today, including our own Milky Way. Each question pulls us deeper into the same central mystery: how the universe. Its first light shaped everything that followed. There's something poetic in this pursuit. We, beings made of stardust, are trying to see the moment stars first appeared. Our curiosity is a form of cosmic recursion matter that became conscious looking back at its own origin. We search for the first light not only to understand the cosmos, but to understand ourselves. Because that first light, however faint, is where every atom that makes us began its long journey. We don't yet know precisely when the universe first lit up. But we do know the light never truly went away. It expanded, it stretched, it cooled, and after 13.8 billion years it still reaches us, crossing the void, whispering of beginnings. When we look at the stars, we often imagine beginnings, the birth of planets, the spark of life, the origins of everything we are. But our story does not begin with our sun. It begins long before, in the darkness that followed the Big Bang. The cosmic dark ages were not just an empty pause in cosmic history. They were the foundation upon which all habitable worlds would one day form. To understand how Earth came to exist and why the universe can support life at all, we must return to that cold, silent era when the elements of possibility were first assembled. Life as we know it requires three essential things: the right elements, the right conditions, and the right timing. During the Dark Ages, none of these yet existed. There were no carbon atoms to build molecules, no oxygen to form water, no silicon to make rocky worlds. The universe was made of almost nothing but hydrogen and helium, the simplest elements. Yet this simplicity was necessary. It allowed gravity to work on vast scales, unimpeded by the complexity of heavier elements. It allowed matter to gather cleanly into stars, whose fusion would forge the very ingredients life would one day need. The Dark Ages were a kind of cosmic incubation, the universe cooling, organizing, and setting the initial conditions for everything to come. Had the universe been even slightly different, if it had expanded too quickly, or if its initial density fluctuations were smaller, the first stars might never have formed. Too fast, and matter would have thinned before gravity could clump it. Too smooth, and there would have been no seeds for galaxies at all. But the cosmos balanced itself with extraordinary precision. Tiny irregularities, just one part in 100,000, became the foundation of cosmic architecture. From those ripples, galaxies and stars emerged, and with them, the conditions for life. When the first stars ignited, they began the process that would eventually make Earth possible. Inside their cores, nuclear fusion transformed hydrogen into helium, and in their final, violent deaths, they created the first heavy elements: carbon, nitrogen, oxygen, iron. Each of these essential building blocks was born in the heart of a dying star. As these first stars exploded, they seeded their surroundings with the ashes of creation. New generations of stars formed from this enriched material, smaller, more stable, and capable of forming planetary systems. By around 1 billion years after the Big Bang, the universe had already begun recycling its own matter, transforming the raw simplicity of hydrogen and helium into the complex chemistry of worlds. The Dark Ages, therefore, were not a void. They were the womb of stellar evolution. Without that long period of cooling and collapse, the universe could never have produced the massive stars that birthed the elements of life. From that first generation onward, the universe entered a self-sustaining cycle. Gravity pulls gas into stars. The stars forge new elements, and their explosive deaths disperse those elements, allowing new stars and planets to form from the enriched gas. This cycle repeated countless times across billions of years. Each iteration increased the abundance of heavy elements, what astronomers call metals. By the time our sun formed, 9 billion years after the Big Bang, the universe was finally rich enough in heavy elements to build rocky planets, oceans, and biochemistry. It took the entire cosmic history before us, all the forgotten stars, all the dust and debris of ancient galaxies, to make one world capable of sustaining life. But elemental abundance is only half the story. The Dark Ages also determined the structure of the universe, how matter was distributed, how galaxies would form, and how stable environments like the Milky Way could arise. If early gravitational clustering had been stronger, galaxies might have formed too quickly, dense. Violent systems where stars constantly collided and supernovas sterilized any emerging planets. If it had been weaker, stars might have remained isolated, never clustering into galaxies, leaving the cosmos sparse and dark. Our universe struck a delicate middle ground. Enough structure to form galaxies and stars, but enough expansion to give them room to evolve peacefully. That balance, set during the Dark Ages, would ultimately determine whether stable planetary systems and life could ever emerge. Another hidden gift of the Dark Ages was time. For nearly 500 million years, the universe did almost nothing visible. But in that stillness, hydrogen cooled and dark matter halos grew deeper. This delay gave the universe stability. When stars finally did form, they did so in environments that could sustain long-term evolution. Without that period of rest, early star formation might have been too chaotic, with stars forming and dying too quickly for complex structures to follow. It's a reminder that even on a cosmic scale, creation often requires patience. The universe waited in silence, so that when light finally appeared, it could last. Over billions of years, those ancient chemical seeds found new homes. They condensed into dust, then into planets, and eventually into molecules capable of self-replication. Every breath you take, every drop of water, every cell in your body carries atoms that were once forged in the first stars. The carbon in your DNA might have come from a massive supernova 13 billion years ago. The iron in your blood may have originated in one of the earliest galaxies. And the hydrogen, the most abundant atom in your body, is primordial. It has existed since the universe's first moments. When you trace life back far enough, it leads not to Earth, but to the Dark Ages themselves, to the time before light, when the cosmos was still deciding what it would become. Even the timing of the Dark Ages helped life exist. If the first stars had formed much earlier, the young universe might have reionized too quickly. That would have stripped hydrogen gas from galaxies before they could form planets, sterilizing the cosmos. If they had formed much later, the universe might have expanded too far, diluting matter so much that star formation became inefficient. Instead, the first light appeared at just the right time, when the balance between expansion and gravity allowed stars to form, burn, and enrich the universe. We often call Earth's orbit the Goldilocks zone, not too hot, not too cold. But in truth, the entire universe passed through its own Goldilocks moment, and the Dark Ages were the threshold. Billions of years later, intelligent life on a small blue planet would begin to look back, piecing together this cosmic origin story. Our telescopes, our physics, our chemistry, all are attempts to understand why the universe allowed itself to become habitable. When we study the Dark Ages, we are studying the conditions of our own existence. Why stars exist, why elements exist, why there can be air, oceans, and thought. Every habitable world, every sunrise, every spark of life is an echo of that first dawn. The Dark Ages were not just a shadow to be escaped. They were the blueprint, the structure of galaxies, the elements of life, the rhythms of time itself. All of them trace back to that silent era when the universe cooled and began to organize. Our planet, our sun, our very ability to ask where we came from, are consequences of decisions made by physics nearly 14 billion years ago. And so, in studying that darkness, we are not looking into emptiness. We are looking into the origin of light, matter, and meaning. In the beginning, the universe was dark. And in that darkness, it prepared for life.
For most of human history, the night sky seemed eternal. Its stars fixed, infinite, and unchanging. But today, we know there was a time before stars, before galaxies, before light itself. And so, the greatest challenge of modern cosmology became this: to see the unspeakable, to find evidence of an age when the entire universe was completely dark. How do you detect light that doesn't yet exist? How do you study an era that left almost no photons behind? This is where the story of human ingenuity begins. The story of how we learned to listen rather than to look. The cosmic dark ages are not something we can photograph with ordinary telescopes. Visible light, the kind our eyes and optical instruments detect, simply didn't exist then. So, scientists turned to radio astronomy, a branch of physics that doesn't look for light but for signals, faint, stretched radio waves emitted by hydrogen, the simplest and most abundant element in the cosmos. You see, every atom of hydrogen can emit or absorb radiation at a very specific wavelength, 21 centimeters. This signal, once short and sharp, has been stretched or redshifted over 13 billion years of cosmic expansion. Today, it appears not as 21 centimeters, but as radio waves meters long. Detecting this ancient hydrogen signal is like trying to hear a whisper across a roaring stadium. Earth itself, filled with cell towers, satellites, and all our man-made radio noise, drowns out that faint cosmic echo. But astronomers persist. They build incredible instruments not to *C* the dawn of the cosmos, but to *it. Some of the first major attempts came from arrays like LOFA in the Netherlands and PAPER in South Africa. These telescopes spread hundreds of small antennas across vast landscapes, each one listening to a narrow band of radio frequencies. Their mission was to detect the global signal of the universe. As first litho moment, hydrogen gas first began interacting with radiation from the first stars. But then, in 2018, a small, relatively simple experiment made global headlines. The EDGES project, short for the experiment to detect the global epoch of reionization, Signature reported something extraordinary. They had detected a dip, a sudden absorption feature, at a frequency that seemed to correspond to a time just 180 million years after the Big Bang. If this was correct, EDGES had captured the first evidence of starlight interacting with hydrogen, the cosmic dawn. But there was a catch. The signal was twice as deep as anyone expected it. This suggested that either something was cooling hydrogen far more efficiently than our known physics allowed, or that something mysterious, like dark matter, was influencing the process. It was a moment of both triumph and extreme caution. The scientific community erupted into debate. Was the signal real, or just some instrumental interference? Others began scrambling to create new models that could explain what might cause such a strong dip in the data. Regardless of the controversy, the message was clear. Humanity had, for the first time, brushed against the silence of the Dark Ages. The difficulty of this work just cannot be overstated. That cosmic 21 centimeter signal is roughly 100,000 times weaker than the radio noise coming from our own galaxy. Separating it from the foreground, the Milky Way's own hiss of radiation is a task of almost unimaginable precision. To do this, astronomers are building experiments in some of the quietest, most remote places on Earth. We're talking about the deserts of Western Australia, home to the Murchison Widefield Array, the Karoo region of South Africa, where the incredible Meerkat Array listens to deep space. And soon, in both of these places together, the Square Kilometre Array, or SKA, the most sensitive radio telescope ever constructed. When it's completed, the SKA will consist of hundreds of thousands of antennas spread across entire continents, all operating as one colossal ear pressed right to the edge of the observable universe. It won't just detect the first stars. It might map the very structure of hydrogen itself as it changed through time, tracing how light gradually broke through the darkness, pixel by pixel, across cosmic history. While these massive radio telescopes listen, other instruments are trying to see. The James Webb Space Telescope, launched in 2021, has already peered further back in time than any telescope before it. Its powerful infrared sensors are designed specifically to detect the faint, redshifted light from galaxies that formed during the universe's first few 100 million years. And it has delivered some major surprises. Within its first months, JWST found galaxies that appeared too bright, too massive, and too evolved for their place in cosmic time, some forming just 300 million years after the Big Bang. These discoveries hint that the cosmic dawn may have ignited faster and more vigorously than our models predicted. In other words, the Dark Ages may not have lasted as long as we once thought. Each new dataset challenges our theories, forcing physicists to revisit the very foundations of cosmic evolution. How fast could the first stars form? Were they truly massive and short-lived, as we believe? Or did small, faint galaxies contribute more light than expected? For every answer JWST provides, it seems to raise three new questions. Across deserts and mountaintops, under quiet skies, and through the vacuum of deep space, the hunt continues. We are listening for whispers older than galaxies, for the faint hum of neutral hydrogen, for the fingerprints of the universe's very first dawn, and every signal, every pixel of distant starlight carries a story not just of matter and energy, but of our own relentless curiosity. In seeking to understand the cosmic dark ages, humanity is, in a sense, searching for its own origin story. Not the birth of life or civilization, but the birth of light itself. Because to understand the universe before the first stars is to understand everything that came after it. The atoms that make up our world, our oceans, our bones, our breath were once part of that same ancient hydrogen fog. We are not separate from the Dark Ages. We are their descendants.
The Dark Ages of the universe ended long ago. But for us, observers born billions of years later, the struggle to illuminate that era has only just begun. We stand on the edge of discovery, between the known and the unknown, armed with instruments capable of probing the universe's earliest, faintest light. The question is no longer asterisk. If asterisk, we can see the dawn. It's how clearly we can understand it, and what it will tell us about our place in the cosmos. The James Webb Space Telescope was only the beginning. With its massive 6.5-meter mirror and infrared vision, JWST has already rewritten our timeline of early cosmic history, but its discoveries have also raised profound new questions. If galaxies appeared far earlier and were more mature than we expected, then the very first stars must have ignited even sooner. That means somewhere, hidden deeper in the stretched-out light of the distant past, lies a chapter of the universe's history we have not yet seen. A time when gravity had just begun to gather primordial gas into the first shining clusters, the first true beacons in the cosmic dark. To find them, astronomers are preparing a new generation of eyes and ears. These are instruments that will work together across different wavelengths, from radio to infrared to X-ray, to build a complete, multidimensional portrait of the cosmic dawn. Take the Square Kilometre Array, or SKA, now under construction in Australia and South Africa. When finished, it will be the largest radio telescope ever built. Its main goal is to map a specific signal from hydrogen, called the 21-centimeter line, across the entire sky. This will allow us to trace how the universe evolved from a uniform fog of neutral gas into the luminous, structured cosmos we see today. The SKA won't just detect the dawn, we'll map it in 3 dimensions. By capturing billions of tiny frequency shifts in that hydrogen signal, it will reconstruct the slow, uneven emergence of the first stars and galaxies. It will show us how reionization, the return of light to the universe, spread like ripples across the early cosmos. Working alongside it will be NASA's upcoming Nancy Grace Roman Space Telescope. It will provide a wide-field infrared survey, complementing JWST's deep narrow gaze with a panoramic view of early galaxy formation. Imagine one telescope giving us a highly detailed close-up, while the other gives us the sprawling wide-angle shot. Together, they'll create an incredible mosaic of the universe's infancy, from individual stars to the vast cosmic webs that connect them. And even beyond these, projects like LAVOIR and Habak's massive future space observatories still on the drawing board, aim to go even further. Their dream is to capture direct light from the very first galaxies, and perhaps even to study the conditions that made life possible on worlds that followed. We are, in every sense, approaching the true horizon of cosmic history. To understand why this search matters so much, we have to remember what first light truly means. It's not just about seeing further into space, because light travels at a finite speed. Looking further out is also looking backward in time. We are reaching back to the very moment when the universe became knowable. Before the first stars, the cosmos was silent and dark. There were no elements heavier than hydrogen and helium. There was no light to reveal any structure. But when those first stars ignited, they changed everything. They were cosmic forges, creating the first heavy elements: carbon, oxygen, nitrogen, thought in the chemical seeds of planets and ultimately of life. Their intense ultraviolet light ionized the thick fog of hydrogen, making the universe transparent for the first time since the Big Bang. And when these colossal stars died, they exploded, enriching the cosmos with the materials from which future stars, solar systems, and eventually living worlds like our own would form. To find the moment of first light is to find the origin of the chemical universe. It's the moment physics became chemistry, and chemistry became destiny. Even now, the light from that first generation of stars is still traveling toward us. Each photon, stretched by the expansion of the universe over billions of years, carries a memory of that cosmic awakening. The universe isn't static. It's a living record, written in radiation and structure. And we, its observers, are learning to read that record, line by line. Our radio telescopes decode the faint hiss of ancient hydrogen gas. Our infrared observatories detect the distant glow of the first galaxies. Our particle detectors study the ghostly neutrinos that escaped when the cosmos was still completely opaque. Every method, every instrument is another sense and a way for the universe to look back at itself through us. Because that's what this search truly is, a mirror turned outward. When we map the first light, we're not just studying the beginning of stars. We're studying the beginning of structure, of order, of possibility. We are studying the cosmic prelude to ourselves. The next few decades will not simply refine what we already know, they could overturn it entirely. If JWST and SCA reveal that stars formed much earlier than our current theories predict, we may need to revisit our ideas about dark matter, gravity, and cosmic evolution. Perhaps dark matter didn't merely guide the formation of structure. Maybe it actively cooled hydrogen gas, accelerating its collapse, or interacted in ways we've never even imagined. Alternatively, if the earliest galaxies appear surprisingly mature and complex, it could suggest that the laws governing cosmic evolution are more efficient than we thought, that the universe was somehow predisposed to form complexity quickly. Each of these scenarios challenges a core assumption about how cosmic order emerges from chaos. And somewhere in that complexity, hidden between physics and time, lies the question that keeps cosmologists awake at night. Did the universe always intend to produce light? Or was it just an accident, a fragile, temporary escape from an eternal darkness? In a sense, our telescopes are time machines. It's not because they move us through time, but because they allow us to witness time itself. Each observation is a reunion across billions of years of conversation between what was and what is. And yet, the deeper we look into the universe's past, the more we recognize something profound. We are not just observers of cosmic history, we are its continuation. The same hydrogen atoms that filled the Dark Ages later came together to form our sun. The same nuclear processes that lit the first stars still burn in our own star today. And the light that once ended the cosmic darkness is now reflected in every spark of human curiosity, in every lens we build, in every question we dare to ask. The universe's dark ages lasted for hundreds of millions of years, but in that immense, profound silence, the blueprint for everything that followed was written. The first atoms gathered. Gravity sculpted their destiny, and when light finally broke through, it began a chain of cause and consequence that led eventually to life, to thought, and to the act of wonder itself. We now know that the darkness of the early universe wasn't an absence. It was potential. It was the silence before the first note of a symphony, the pause before the first sunrise. And when that first light appeared, It did not merely brighten the cosmos, it made it possible. Somewhere out there, light from the very first stars is still on its waist, crossing the void, still whispering the story of how everything began. We creatures born of that light are waiting to receive it, to hear the echoes of creation, to see the universe as it once was, and to remember that even the brightest dawn begins in darkness. Thank you so much for joining us on this journey to the edge of time. If you found this as fascinating as we do, please consider liking this video and subscribing to the channel for more explorations into the cosmos. See you next time.